Let's move up. We got some quality seats up here. Quality seats. You want to move up here? We got quality seats. Okay. Have a good time with the kiddos. Okay, focus with me. What was our general scheme on how to draw an electron dot model? What was the little saying we wrote? With me. VSEPR, valence shell electron pair repulsion. What did the V stand for? Valence, count valence electrons. S, with me. Skeleton. You had to create a general format of what the format or the molecule looked like. This one? Add electrons until what? Octet. You want to make sure you get octet on everything, except for hydrogen, because it's little. It doesn't attain. It doesn't make octet. It's got a smaller radius. Pairs, and pairs could have meant lone pairs, or you could have made something a double bond or a triple bond. Okay, so you could have adjusted the pairs and where they were located. And the last bit is just review, right? All right, so that's the general rule of thumb. There are a couple caveats though, because some of you guys were starting to look at the dot models for the lab. And you're like, I got 36 electrons. I've got all this extra stuff. What do I do with it? So this is the more expanded version of it. But tell me what each of these represents, and I'll tell you the last thing to write down for us. Okay? Total valence electron group. That's just V, right? Choose central atom. This is starting what? What part of the steps? Skeleton. All right. So the skeleton actually is going to be choose central atom and add your bonds, okay? The central atom, here's a good trend or a good method to follow. If you have carbon present, carbon is going to be the center, okay? If carbon's not present, let's say phosphorus trichloride. Carbon's not present, you just choose the singleton. I'm hoping that people in the back are listening because I haven't seen their eyes once, thank you. Largest atom is going to be the next one. So if you have two singletons, let's say OFCl or something like that. Cl2. Who's your largest?
Oxygen.
Yeah, oxygen. From the two singles, the oxygen's your largest, so that would go in the middle. So that's kind of the way, the prioritization of how you would figure out the central atom. Distribute the rest of the electrons, that's E. Satisfy octet rule. Complete octet on the central atoms at least, try to. Distribute pairs of electrons among the ligands so that you have like kind of a symmetrical shape here. This is the last thing that we didn't talk about yesterday. That's the one that you need to know and or write down if you want to. If you have more electrons, and you've already gotten every octet to everybody, you've already got duet or 2 to hydrogen, you still have more electrons to add. You don't know where to put them. Put them on the central atom. They're lone pairs though. They're not like a bond. They're not going to make a double bond because then that's going to make somebody else have more than octet. You can't do that. So you only want to add them to the central atom as lone pairs. And I'll draw one of them like your, let's see here, I think it's the fifth one down on your model sheet. What is that one? Live. Fourth one down. Are you spelling, hey, S-A-R-A-H? Name it. I don't want to spell it out. Xenon tetrafluoride. Thank you. Use your real words, people. Okay. Xenon tetrafluoride has how many electrons? 8 plus 4 times 7. 28. So 36 valence electrons. Okay. Who's your central? Xenon. We have 4 ligands. I'm drawing this one for you, so hopefully you're drawing this with me. It's on your lab sheet. Fourth one down. Some of us are zoning out. Okay, that's on you. Adding octet everywhere. Need another lab sheet? It's all yours. It's just stapled. Okay, so we got octet everywhere. Everybody's happy, right? How many electrons have I used thus far? 32. I've got 8, 16, 24, 32. So I've got 2 more to add. So what I'm going to do is I'm going to actually add them to the central atom here and here. Just do it symmetrically, so opposite of each other like that. I have a hard time seeing your dots sometimes. So if you can make them really bold, that'd be great. Or you can actually circle them to say, hey, they're right here, miss them. You can't miss them. Because sometimes I take off for stuff if I can't see it. Make it very obvious for me. All right, so that one, I want you to look on your little cheat sheet, the back of the electronegativity sheet. Most of you guys have one probably accessible in the near area around you. It's their electronegativity sheet. Tell me, is there a shape for that one? How many ligands are there? 4. How many lone pairs? 2. Is that on the sheet? No, it's not on the sheet. Thank you. So it's not on the sheet. So that's why this is called something called expanded octets. Okay? Expanded. This is the last part of the. Well, we'll do some more examples together. This last part, like the notes for right now. Expanded octet only occurs for any central atom that is 3p or lower. So, give me some examples of elements in 3p. 3p, third row, p block.
Silicon.
No.
Wait,
That's silicon. 3p. Sulfur. Okay, aluminum is not going to make a central atom because it's a metal, right? It does not share. We're talking covalent here. Phosphorus, chlorine, argon, and then anything below that, so or lower. So let's go. Bromine is a common one. Krypton is another one. Xenon. Okay, so you see a lot of the noble gases, they actually do form central atoms, even though they don't really need to share, but they like to, they like to be good citizens and share with the other little lonely elements that need some help. Okay, with octet. So a lot of times if you see these guys and they're the central atom, they will have expanded octet. That's because here's the reason. Because they have access to 3D or 4D or 5D. Okay, so 3P technically is in the same energy level as 3D, right? 3P, 3D, they're in the same energy level. They can actually throw some extra electrons in those 5 orbitals that D block contains. They don't have the electrons themselves, but if they're sharing with somebody and they have access to it, they got 5 extra pockets for those electrons. They can have that, they can do that. But like nitrogen, you'll never see over octet. Oxygen, fluorine, never. Carbon, never. Because they don't have that. They have they're in 2P. Is there such thing as a 2D? No. So they don't have access to that. That's why they only do octet, while some bigger, better atoms can do expanded octet. Okay, that shape. Let me draw this for you. 3D skills. Here we go. Xenon kind of takes on a, what's that shape? That looks like a trapezoid, right? Ribosome, something like that. Not ribosome. Rhombus. Oh gosh, that was great. Okay, that's actually what it ends up looking like. Okay, it's flat with 4 different ligands front and back. Huge lone pair on top, huge lone pair on bottom. If you build this, all you see are those 4 corners. It's a flat square. Guess what we call that? Square planar. Because it's a plane. Square planar. There you go. I got you through what? The 4th column in that one? Yeah? Square planar. That's not on the gray sheet, so that's why I want to make sure you wrote that down. Okay, so let's do some more examples together because I need to do some varieties. We did a lot yesterday, but I want to do at least 3 more today. So these will just be notes. These will not be on your molecular Lewis structure sheet. Okay. We got through those yesterday. We didn't do this one. What's the name of that top one? Did we do that top one? Carbon. It's organic. How do I know it's organic? It's carbon and hydrogen. So generally carbon and hydrogen together, you name it organically. Can you name that? That is ethane. Thank you. Good job. This is ethane because there's F, 2 carbons, and then 2N plus 2 to get to 6, right? Ane. Ethane. What if I had said C3H6? I heard prop because prop is a good one for 3 C's. Propene because it's 2N. Straight just 2N. Propene. We'll do some more practice with those. Those are just kind of exclusive. Okay, so that's just naming it. Now let's go to Lewis dot model. First step, V. We're going quick here. How many valence electrons?
4 times.
4 times 2 plus 6 times 1 total. 14 valence electrons. Okay, now who's the central? Carbon, but there's 2 carbons, right? So they're both central. Remember we were drawing on those long carbon chains yesterday? So essentially this is a short carbon chain. It's only got 2 carbons. So how many bonds do I need around each carbon? 3 more because they already have 1, right? So each carbon requires 4 bonds. With me, Jeremiah? I'll take it. Work with me. 3 carbons. Ooh, that one's ugly. Whew. 3 carbons. Hydrogens around each one. How many electrons are on carbon? How many electrons? Those are 4 bonds.
No, I have a question.
Yeah.
You say each bond counts as 2 electrons.
Mm-hmm.
That's 4 valence on every
This?
Yeah.
Yeah. It has 4 valence electrons to donate to this worthy cause of making this molecule. The whole reason for bonding is because you want 8 electrons around you. You give 4, you take 4, or share 4, that means that you get an octet.
Oh, okay.
So that's the purpose. We don't bond just for kicks and giggles. We bond because we want 8 valence electrons total. So this carbon has 8 octet. This carbon has 8 octet. Each hydrogen has 2 because it's sharing. Okay, remember, sharing doesn't mean you get to take it. It's just it's a shared space. So each hydrogen's happy. Total valence electrons listed here. 14. 2, 4, 6, 8, 14. Okay, so that one doesn't have a specific shape because we don't have one central atom. If we don't have one central atom, it's really hard to give it a shape. Okay, next one. So that one's just a carbon chain example. We did nitrogen yesterday, so I'm going to skip this slide. Let's go straight to ions. Okay, let's do these 2 ions. Sulfate. Give me total valence electrons. Give me your process.
7, 6.
6 plus 4 times 6 plus, what does this mean?
2 more electrons.
2 negative charge means you've got overall 2 extra negatives. That means you have to add it. That's going to be a weird one. You'll see one like that on your test. I'm trying to do you guys some examples of everything. So total, that's 24 plus 6 plus 2, 32? Yeah? Yeah. So central,
Yes.
sulfur with 4 bonds because you got 4 other atoms to account for it. So far I've used 8, so I need to put octet on everybody else. So I'm adding electrons here. Okay, how many electrons have I used thus far? 32. I got 32 to work with, so I've used 32. The only thing that's different about an ion is you have to show me the ion charge by bracketing it off, like we did with our ionic stuff, and putting the 2 negative charge on the outside. It's the only thing that's different when you draw an ionic structure. So, fancy polyatomic ions are ions, but internally, they have what kind of bonds? Covalent bonds. So polyatomic ions are actually covalent ions. That's a weird one, okay? So anyway, this is 90% right. In AP chemistry, we'll do like more with this, but I'm sticking with that for now. Oh, what's the shape of this? Central atom has how many ligands? 4 ligands shape. Tetrahedral. So that looks like a tetrahedron structure. All right, same thing for this one. What's different though? We have a cation. What do you want to do with my valences? -1, right? So nitrogen has 5 because it's in group 5. 4 times what for hydrogen? 1. And then overall, -1 because it has a cation charge, so it's overall losing 1 electron. So 8 valence electrons, what's it look like?
In the middle.
And in the middle,
4 bonds.
4 bonds. How many electrons have I used thus far? 8. What's still wrong with this? Bracket, right, because it's an ion, has a +1 charge. All right, so you get the flow of this really well. Yeah.
Did you put the ligands thing again?
Ligands are, you only look at central atoms. Central atom here, I always think of ligands as legs. Okay? They're just attachments of atoms. Just atoms. So this one has 1, 2, 3, 4 atoms attached to it. So it's got 4 ligands, 0 lone pair. If by chance this is wrong, if by chance nitrogen had a lone pair here, then the lone pair, thank you. Have you made a copy of yours for yourself? Awesome. The lone pair here would account for something else. So we'd have 4 ligands and 1 lone pair, and that will cause a specific shape. Question? Yeah. Thanks. Watch the rest of this video, okay? Yeah. I get from drawing it.
Like if you look at NH4, which one do you choose?
That's what I was just going over with the expanded rules that I was just going through. So there's our short rules, real quick and easy, but then we have those caveats of how do you choose a central atom? If carbon is present, it's carbon. If you have a single, no carbon, if you have a single thing, like I gave you that example, this one I have 3 chlorines, can't really pick from that, so you choose the one that you have a single atom of it, or if you had 2 single atoms, you choose the larger of them. So it's like kind of a priority list. But a lot of times it's just we have a singleton, so you just choose the single. Okay, you try to make it symmetrical. Okay, I think it's the last one I'm gonna do. Yeah. Oh no, I want to do an expanded octet. Oh, we just did an expanded octet. We're good. Okay, so for VSEPR, tell me of this. What did we not explain yesterday? What did you not hear about yesterday? What doesn't seem familiar anyway? Huh? Molecular polarity. Where's that at? Where did I put that? Do you see molecular polarity on there? Okay, but we're going over molecular polarity after we do the lab. So I was like, did I put that up there yet? Not yet. Okay, I'll get there then, okay? But from this, we said this guy, VSEPR valence shell electron pair of repulsion is causing the atom to shift around the bonds because those big, huge lone pairs are repelling. It's going to make a shape. That shape we've been practicing a lot so far. The last thing that I don't know if I mentioned was the bond angles between the ligands, they'll change. So tell me, what did I tell you the bond angle of methane was yesterday? What was it? Oh, yeah, it was a ballerina. What was my bond angle? It was 90. 109.5. Good job. Okay. So that shape is what though? Shape. Tetrahedral, right. It looks like I'm drawing 90, but in 3D space, it's 109.5. Ammonia, NH3, looks like this. What is this lone pair up here doing? Pushing them down. What was the angle that I said here? Did I say one yesterday? Well, what do you think is going to happen? Is it going to get bigger or smaller? Smaller. So between tetrahedral at 109.5, this one these bottom three push together a little bit, and it's going down by 2.5 degrees, so it's 107 degrees between these guys here and these guys here. Okay, now let's go one more down. Let's go to water. Water, H2O, makes a shape like this. Okay, two huge lone pairs. What do you think is going to happen between this angle? How much smaller? 2.5 lower, so 104.5. Good. Sounds like we're like shouting out radio stations. 109.5, 107, and 104.5. Okay, so, we can make a rap with that. Okay, so anyway, basically the trend you see is as you add more lone pairs, what happens to the bond angle? It gets smaller, okay? That's basically what I want you to see, and we'll do some more of that later. But let's go ahead. Let's build some stuff. I'm going to check your stuff you built. You're going to make sure that you fill out the first 4 columns of the lab sheet, and then we'll come back and we'll do molecular polarity together, and then hopefully finish the lab. Deal? All right, Miss Limo. All right. Let me show you back here. You guys work in groups of, I'd say, 2 or 3. I have 10 molecule kits. Okay, come on back. Grab a partner. Go see Rose. Bring the electronegativity sheet with you. My station. There's gray boxes. Go see the gray boxes. You guys, there's a station here. I'll give you this one. Oh, look, there's one right here. Yay, okay. So, guys, look at that. There's a little cheat sheet in front of there. What color is carbon? Open up your kit. What color is carbon? You need no guess. Look on the sheet. Anna, hold up the sheet we're looking at. Anna, thank you. The sheet says it's black. Alright, I'm going to wait on you because if we can't listen, then we ain't building. Okay, carbon, pick up the black one. Carbon, how many holes are on it? 4. That's because carbon likes to form 4 bonds. Let's say you wanted to show me that you had 4 ligands and 1 lone pair. I need 5 holes. Which one has 5 holes? Which color B? The tannish brown one, right. So if you ever need to use 5 different spots, you gotta pick correctly. What is a halogen? What color is a halogen?
green, that's the little single one on the outside. Okay, there's little tiny green dot ones. So just make sure you're choosing appropriately and how your shapes will look like. Alright, as you build, maybe call me over every 3, not check them all at once. Do not deconstruct until I check your shapes. Go. Guys, you gotta draw these before you build them. How many bubbles you need?
All right. I'm gonna scroll down again in a second. I promise I'll come back. Okay, so I'm gonna scroll back down in a second. Let's talk about the two different types of polarity we've spoken of. Is bond polarity, which is just simply a covalent bond. One side's got more electrons than the other just because they're different electronegativities. The two versions of that are polar covalent bonds and non-polar covalent bonds. What's the other type of bond? Ionic, right? That's why I say polar covalent, not polar covalent, because that means I know you're talking about a bond. But if you just say this thing's polar or this thing's non-polar, I hear molecular polarity. I'm thinking about a molecule as a whole. If it's like a big sphere, you know, it's got stuff all around it. Let's say fluorine, 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 fluorine. Where were these dipole moments on your model pointing? Your lab you just did? Who was more electronegative? Fluorine or carbon? Fluorine, okay? So this is a tetrahedral structure, right? Your dipole moments on your Lewis dot model as you guys are going, you should have pointed them outward, 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 and downward, okay? So essentially what it's showing you is that the electrons are being pulled north, south, east, west, or, you know, in the tetrahedral appearance, equally. So there's negative charges kind of everywhere here. So is there any opposite ends? Are there opposite ends, period? Do you see a positive area and a negative area? No. So around the whole shebang, you got negative, 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 negative. That means the whole molecule is nonpolar. So if you say NP, that means a nonpolar molecule. And it's due to the geometry. Because what happened was the fluorine here, 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 and here canceled each other out. The fluorine up and down canceled each other because they're pulling opposite directions. And the fluorine left and right cancel each other because they're pulling opposite directions. But if you have something like water, it's bent, right? H2O is bent. The dipoles point which way? From hydrogen to oxygen or oxygen to hydrogen? Right, oxygen's more electronegative. They point upwards and upwards. So what happens is the electrons are kind of shifted to the north, leaving a lack of electrons in the south. So the lack of electrons down here make overall the bottom part of this positively charged or partially positively charged, and the top of this partially negative. So do we have opposite ends here? Yeah, so it's polar, like a north and south pole, like the globe is polar. All right, so if I put this through a magnetic field, it's going to align north and south like the magnetic field indicates for it to. It's going to be attractive. This, it's going to go right straight through a magnetic field. It has no attraction whatsoever because it doesn't have any opposite charges on the ends, okay? So what I was trying to show you is that it depends on the dipole moments, meaning like a polar covalent bond, and it depends on the geometry. This geometry, if it were straight, linear, one going one way and one going the other way, or both of them to the middle, they actually cancel each other out. Either go to the middle or to the outsides because they're opposite in direction. But because it's bent, it does not allow for the cancellation of those dipole moments. So what's another shape that you don't think is going to allow for cancellation of dipole moments? What's another shape? Ammonia.
Pyramid.
Pyramid, thank you. Ammonia's got that nice pyramidal structure. So it's got a lone pair up here, and it's got that H, H, and H down here. So what's happening is these dipole moments are pointing towards nitrogen, towards nitrogen, towards nitrogen. Sorry, it's way over here. And then we got a hugely negative region up here, and a very positive region down here. So that's going to make it a polar molecule. That's the fourth or fifth column on your lab, okay? So for you to know that, you have to know both the bond polarity. So if they're polar bonds, you have to defer to the shape to see if those polar bonds cancel each other out. If they can't cancel each other out, you've got a polar molecule. So that's why the geometry is very important to be able to visualize and build and draw and, you know, read so that you can determine if the polar bonds cancel each other out or not. Generally, if it's a nonpolar covalent bond, generally the lone pairs, oh my gosh, please start reading guide. I'm sorry, start problem set 7-8. It's not due Monday, it's due Tuesday. Bye. Sorry about that. I'll finish this Monday. Start problem set 7-8. Just start it. Pre and